Hello, and thank you for joining my webinar on signal detection theory, exploring the false and miss. I'm honored to be here to speak to you all again, and thank you very much for hosting me. So today we're going to be talking about what is signal detection theory, and how can we apply it to our detection dogs, and what important implications does that have for the prevalence of things like false alerts and misses. So I've decided to dive into different PowerPoint templates that have come out in the new version that I've downloaded of PowerPoint. So I'm trying this one out for a go. And with that, it suggests that we provide on the second slide a very clever quote to get you thinking. So I had to just come up with one, which is, sorry, this is going to be technical, which was said by me just an hour ago. So I put this together and I realized that this this PowerPoint show gets into some pretty nitty-gritty details that I think will be important and interesting, but I'm sorry, there's going to be lots of graphs. I tried to keep the math to a minimum, but there'll be sort of lots of graphical exploration of trying to talk about fundamental topics. And I hope I bring you along with me throughout it all. If not, then please ask as many questions as you can during the Q&A part of this. Okay, so key concepts that I want you to walk away from here today is going to be understanding what is noise, other than simply sound that you hear. What is noise in terms of a signal detection perspective? What is a signal in terms of a signal detection perspective? What is this little funny character D prime? What is our criterion or bias? And then better define what is a false alert, a miss, a hit, a correct rejection, which are basically the four categories that make up signal detection theory. And then ultimately prior probability. Okay, so let's talk about some of our definitions first. So here, our first series of rows are going to be sort of the true state of the world, whether an odor is truly present or an odor is truly absent. And then here is what the dog's performance is. So does the dog alert or does the dog non-alert? So if the dog alerts and the odor is truly present, this is called a hit. If the dog alerts and the odor is truly absent, we call that a false alert. If the dog does not alert, but the odor really was present, then the dog therefore misses. And if the dog doesn't alert and the odor was actually not there, this is also a correct answer, but we call it a correct rejection. So these are the key terminologies that will be coming up over and over again in signal detection theory. So let's dive into that a little bit more. So the first concept that we want to discuss is noise. So noise is kind of like as it sounds, and perhaps as you're looking at this, you kind of almost automatically hear a ch in your mind, looking at this white noise picture probably from your TV. So noise is all around us. Pretty much all of the signals in which we have to detect one way or another, whether a light is green or light is red, the number 2 versus the number 3, all of these things are the signals that we're trying to find, but they're occurring in a sort of moving background, a noisy background. And that noise is coming from all different directions and all different types of input. But it's an important concept to think about because that's going to come up over and over again. So this is an example of sort of a machine version trying to interpret handwriting. So this would be zero noise situation, 0, 3, 6, 9. And then this is those same numbers, but with varying levels of noise in the background. Different sort of drawings of the zeros, of course, with different levels of noise. And as you can see, by the time you get to 50% noise in the background, it becomes much more difficult to actually correctly decipher what those numbers are, and it becomes particularly difficult for computers to do that. But as you can see here, this is sort of the classic example of what we would call noise being white noise. If you're really into noise, There's actually a variety of different kinds of noises. There's brown noise, pink noise, white noise being one of them. I'm not that into noises, so I'm not going to explain the difference between them because I don't know, although I think it's pink noise people are supposed to like more than brown noise. Anyway, it doesn't really matter. The purpose of it is that noise is basically this kind of fuzziness that's going to be overlaying the signal that we need to detect. Where a lot of the original research that we're going to be interested in came from is actually mostly from having to scan manually radar screens, right? If you think of the radar screens from World War II, you're looking for these little tiny kinds of blips, and there can be lots of different things that would produce things that might look like something that you need to detect, but are really just noise in the system. So how do you detect from a potentially noisy background the signals that you want to find? And signal detection theory is one of the key ways that sort of defined that in a mathematical sense that we'll be discussing more about. But let's dive a little bit more into our concept of noise before moving on. So here's another sort of example of noise. Here's a picture. This is sort of what they're calling here the ground truth. And this is ultimately, this came from a paper looking at trying to reduce noise from a programmatic perspective. As you can imagine, these kinds of tasks are really important in engineering. These are also the kinds of tasks, like if you're into CSI shows, right? And the suspect is gotten away, but you have CCTV from a gas station, and they look at it, and the car is like 2 miles away, and they pull up the video, and they just say, enhance to the computer. And then they say, enhance again. Well, what that computer in theory is doing, although obviously it cannot do what they show that it does, is basically it's removing the background noise and trying to fill in the image, which is what's being done here. As you can see, with the particular algorithm that was in this paper, they were able to take this highly noisy image that has sort of noise built in, and we can assume that that noise comes from the way that the picture was recorded, is something to do with the film. But nonetheless, you can see that you get a pretty darn good picture. Nothing like the original here. It's still pretty blurry, but they were able to remove a substantial amount of the noise that you can get. Sort of, maybe perhaps you could get the license plate number out of this. I don't know. But nonetheless, the purpose of this is to highlight the fact that perhaps you are a koala detection dog, right? And in some environments, there may be little to no noise. In some environments, there might be sort of some noise. In some environments, there's going to be lots of noise. And your ability to detect the target that you're looking for, whether it be visual or olfactory, is going to depend on what that background noise happens to be. If the animal is looking only in this highly noisy background, then obviously you can imagine that the detection task is going to be a lot harder. And when it becomes harder, there's going to be a higher probability of mistakes to occur. Okay, I told you at the beginning that we were going to dive into this graphically a little bit more, so here we go. So these are just some graphs that I made just for this purpose, particularly nothing else, where I just have X, which is meaningless, just something arbitrary that I fitted. Y is also meaningless, arbitrary, something that I fitted. But the purpose here is that I sort of defined a ground truth relationship, which is this sort of linear line with a slope of 2 and an intercept of, I think I defined the intercept at 0. Looks like it's at 0. It might have been 1, but anyway, at 0 nonetheless. So this is sort of the ground truth of the real sort of function, or the real thing that is occurring. And then basically I just added different levels of noise in an increasing pattern as we go off to the right. So as we go here, you can see that the pattern still holds, right? As I add a little bit of noise, as I add some more noise, the pattern is still kind of there, but it's a bit more fuzzy. As I add more noise, it gets even more fuzzier. And then when I add extreme levels of noise, that pattern now is undetectable. In fact, I would think that it's something like a straight line here. So here, having substantial noise completely masks and prevents detection whatsoever of what the underlying pattern here is. Here the noise doesn't help, but you would still find something like a line like that and a line like this. So here this noise doesn't help, but it's quite separable and you can still see the underlying pattern, which would be similar to in these levels of noise you can still detect the target, but it becomes increasingly more difficult. And it means that because of this noise in the system, there's going to be more propensity for errors. And then by this point, there's probably going to be high propensity for errors, and the fact that you may not even be able to have any sort of successful detection system in such a noisy background. Noise can be external or internal to your system. So the noise can be internal in that it could be related to the dog's sensory capabilities. So say, for example, a dog goes on some type of medicine, right, that might influence the olfactory receptor performance that is increasing noise to that system. It could be very external in the sense that there could literally be extra noise. Perhaps the dog is working in a noisy environment where maybe there's gunfire in the background or something like that. Or it can be external in that maybe the dog has to work around a lot of other dogs, or an environment that is noisy from an olfactory perspective, that there's lots of other odors in that environment that can be distracting and potentially mixing with the target odor, increasing the overall noise there. So the point is that noise is quite substantial, and it's going to have a very significant impact on the overall dog's performance, regardless of how good the dog is or how well trained the dog is. These are sort of ultimate factors about the underlying condition of the task that we're asking them to do. So our analogs within an olfactory setup would obviously be working in a smelly environment. So if you're asking the animal to do a detection task in perhaps an environment that includes lots of other smells, then that's going to be much harder because those other smells are going to act as noise and will subsequently interfere with the detection of what you're looking for. Or perhaps maybe the target odor is contaminated with many other components. Maybe it's mixed in with a lot of other components. And ultimately, that's what white noise is, right? So white noise is the product of a variety of different frequencies coming together and sort of all mashing together. In the same way with color, right, is the overlap of a variety of different colors here. This is the color sort of mixing that you get when you're mixing like actual colors, not the spectrum, which is why this is sort of overlapping here in this pattern. But anyway, so as you mix multiple colors together, you start to get unique colors, but then eventually when you mix them all together, you get black. And then think of this from an olfactory perspective would be more like soup, right? Imagine you started adding in one ingredient, another ingredient, and another ingredient, and then perhaps you get up to a point where you have 50 to 60 ingredients. The individual impact or your detection capability of one of those ingredients is going to go down, sort of the more other components are within that. And there's actually some papers about that, or particularly one key paper looking at that in humans. We haven't really looked at this in dogs yet. And this here is the hyperlink, so that if you have the slides, you can just click on this or copy and paste this over, and this will bring you straight to the paper. It's a good paper, it came out a few years ago. But what they found is that essentially they did this kind of soup experiment where they added one chemical, then another chemical, then another chemical, then another chemical, and asked essentially what does it smell like. And what they found out is that once you add about 30 chemicals, it doesn't matter what the identity of those chemicals are. It can be any 30 chemicals. But once you sort of added in 30 chemicals, you started to produce this kind of white noise smell. This smell that becomes indistinguishable from anything else, and that 30 components of these set of components, and then another 30 set of components of these components that have no relationship to each other. Once you mix those together so that you have this 30 component mixture and this 30 component mixture, they actually begin to smell quite similar. So perhaps there's actually a white noise smell in the sense that it's the combination of multiple components coming together. So in that situation, if your target odor is mixed within that 20, 30 number of components, then perhaps you ultimately are producing this kind of white smell. It doesn't really smell white per se, but it's this smell that is ubiquitous to or similar to our white noise, which is the combination of a variety of different frequencies. In a common situation where a lot of these issues also come up, particularly with noise and detecting a particular signal within these noisy background, is with TSA, Transportation Security Administration, which that's what we're called in the United States. Are they called that everywhere? I don't know. I should have looked that up before this, so my apologies. But anyway, the people who screen luggage bags before you get onto an airplane. So it's quite a complicated task, and it's a hard job, right? Where their job is to look into this bag that has a bunch of noise, right? A bunch of sort of squiggly lines and things like that, and be able to try and identify and detect key things. So what this one is detecting are lighters, and I believe all of these boxes are highlighting potential lighters that are being detected, which indicates that this bag has too many lighters and needs to be pulled aside and examined. This bag has these pliers here, but otherwise doesn't have anything else. I'm not sure if you can ply with pliers or not. But anyway, the point is that right, they have this sort of noisy background with a variety of things going on, and the job is to try and detect these little signals. And not only do you have the noise that's sort of built into the system, right, that these bags are all producing varying levels of noise. You have the noise from the X-ray machine in of itself, but you also have the actual ambient noise, right? You have people asking them questions, you have people walking around, you have distracting things that are occurring in the airport, and all of these are sort of increasing that noise, which makes it all the more difficult to try and focus on that target that you're looking for. And the same can be for our dogs, right? The dogs are operating in similar environments. Well, there's a lot of other noises, lots of other smells that are going on that can all be distracting in one way or another, producing this undesirable levels of noise that we don't particularly want, that makes the detection task more difficult. In some cases, the signal can actually be decently obvious, right? So in this case, I think there are a couple of things that would be easy to find. So one would be a computer, right, or batteries. Maybe that's what they would find, would be the batteries there. But obviously two other objects would be your target here. So moving away from the noise, what we actually want to find is our signal. And I'm sorry if all of the red pen gets you upset. I get particularly obsessed with the red pens, so I use it a lot. But anyway, you have the signal that's quite obvious in this case, and that's what you're trying to detect. So you have all of this noise, right? And here you have very little noise, but you have some noise. You have this noise in your image, and you're trying to detect your signal amongst all of that kind of noise. So in our situation would be detecting our target odor and the noise of, the ambient environment. So if you're doing a search and rescue situation, not only do you have the potential odor that you're looking for of the person, you have the odor of everything else that is occurring there. Perhaps it's under rubble conditions, right? You have all of the odors coming from the rubble, and that is all of your background noise, quite extreme background noise. And what you're trying to detect is that particular signal or the smell of a person. Sort of where some of the research initiated was looking at targets on a radar screen. And then again, in a sort of a more naturalistic setting, which was also potentially applicable to dogs, is trying to identify the location of prey amongst sort of, the jungle or savanna or the desert or the mountains, any sort of situation where you have lots of visual noise or olfactory noise, and you have to identify where your target is amongst all of that noise. Okay, so here's where we get a bit more graphical in our representation of signal detection theory. So what I have here is a figure where the y-axis is our sort of a density function. So if you're not familiar with sort of Gaussian distributions, then let's not worry about that too much. But well, first, this is a distribution, and what this distribution is just highlighting is where is all of your data in response to sort of some internal response. So basically, where this peak is, this is where most of our data lies right here. And as we go further and further out, we get less and less data or results occurring over here, less and less data over here, less and less results over here, and you get it the same way here. So most of our data is focused right in this particular central area for this noise curve. And then we also have what I'm calling our signal curve. So here is the noise, which is all that background white noise that we were talking about. And here is our signal, which is going to be what we're actually trying to detect. And then this is where most of all of our signal is. And we have a little bit out here and a little bit out here. But by and large, nearly all of our signal is over here and all of our noise is over here. And what we can do is we can calculate, well, what is the distance between our signal distribution and our noise distribution. And that value here is d prime. There's actually a way that you can calculate this mathematically by taking the performance of your dog on a detection task. Usually it would be a go, no-go task, which would be something like, which is what we would typically do. Sniff this container, is there something here or not? Sniff this container, is there something here or not? Sniff this, is there something here or not? Sniff this, is there something here or not? And then there's a way to turn that data into a noise distribution, a signal distribution, calculate d prime to determine the overall discriminability that particular odor is in that sort of situation with that noise distribution. I'm not going to go into that specifically today. There are great tutorials on that when you search for signal detection theory, but I viewed that probably as too nitty-gritty mathematical for the purposes of this particular webinar, but perhaps we can dive more into that in the future, or definitely something worth looking at, so you can get a sense of what perhaps the d prime value is for your specific detection task that you're interested in. So why do you want to know the difference between these two distributions? Let me dive into why that's potentially important and what impact that has. Okay, so here we have the graph that we were just playing around with our signal and noise distributions and our d prime. And then here is another figure which is showing the exact same, our signal and noise distribution, but the key is that our d prime is a much smaller number. The distance between these two peaks is much smaller than it is over here, which means that the discriminability is quite different between this condition, where your signal is way out here and your noise is over here, and this condition where your signal and your noise actually show substantial overlap. The reason why that is important is that when you get overlap between your distribution, that is where your errors occur. So right here, this is where the errors occur within your detection task. However, over here, this is where your errors occur within your detection task. So as you can imagine, when your d prime gets smaller, the frequency of different types of errors, so misses and false alarms, are going to be increasing quite substantially. So knowing what this d prime is will tell you what are going to be your expected rates of false alarms and misses within your particular situation. This also highlights that it's really important how far off your noise distribution is from your signal distribution. So situations where they can be quite far is, say, for example, like the picture of the bag with the 2 handguns in them, right? That were very easy to see. There was no confusion. There was very little noise, things that were on top of them, making them hard or obscure to see. So this would be a situation where we have a very large D prime. It's very easy to detect something. This could be a situation where perhaps you're using, in the sports area, you're using essential oils. They are particularly strong, highly volatile odors. So they're much easier to detect against the noise of the background of your environment. So these would be high sort of D prime tasks. Small D prime tasks might be situations where the dog is detecting explosives with very low vapor pressures, which means they're giving off very little odor. Or perhaps it could be a situation where maybe the detection task itself is not difficult, but the noise distribution is very, very large and sort of somewhat overlapping with our signal distribution, because there's so much odor background noise in that situation. Or perhaps you're looking at mixtures for odor explosives where the noise background, things like sawdust or different types of potential fuels, are going to be your noise distribution, and your signal distribution is going to be highly overlapping with that, because it's basically your potential target mixed with a lot of those fuels, which sort of shortens down your D prime quite significantly. So D prime tells us about how far 2 distributions are. As you can see, our D prime, the difference between our koala and our background, this would be a situation where we have our small D prime, very sort of high overlap between koala to background, or background noise, sorry. This would be increasing D prime, where it becomes very easy to detect the koala because the background noise is signal distribution, or sorry, noise distribution is quite far away. And then here it's very easy to detect the koala because our noise distribution is extremely far away. So this would be a much higher D prime. And if I were to ask you, is there a koala in this picture? Probably no one would make a mistake here, but people might make mistakes over here with the smaller D prime. So D prime tells us how far apart these distributions are, which also indicates how likely an animal or humans are animals, but anyway, the animal or your dog might have difficulty within that detection task. So that sort of largely encompasses what D prime is, but there's another variable that's quite important in here that will ultimately determine that not so much errors overall, but that ratio of false alarms to misses that you will make. So criterion is basically a simple way of saying, well, what is that internal sort of mark that you have inside of your head that tells you that I'm going to respond and say, yes, a target odor is here. I have smelt enough to formally determine that a target odor is here. So I have a little clip in here. Perhaps some of you might remember going through hearing tests, going through recently with my son. They're very different now than what they used to be. But this was the hearing test that I was familiar with.
Okay, gentlemen, I want you to raise your hand.
So the point is if you remember doing those tests, so perhaps you remember from doing the hearing test yourself, you have to decide when do you hear the tone and raise your hand. And perhaps some of you are what we'd call very conservative. You would be like, I think I hear it, but I'm not sure. I don't really want to raise my hand. I pretty sure I hear it, but I'm not terribly sure, so I'm not going to raise my hand. And you're like, now I hear it. I'm 100% positive that I hear it. Whereas other people are sitting there and they're like, yeah, I think I hear it. Yeah, I think I hear it. And they haven't even started the test whatsoever yet, right? So those would be what we consider liberal criterions within the task. And signal detection theory is here to actually try and define that mathematically and determine the difference between our more conservative and our more liberals in terms of how likely you are to indicate whether you detect the target. So here is our figure from before. Here is our sort of larger D prime. And then we have here our criterion level. So we have an internal kind of criterion response level that if we feel that we have detected the signal, whether it being a dog detecting a particular odor or us hearing the sound for the hearing test, and it is greater than this criterion threshold, that our feeling that we hear it is greater than this value of C, then we raise our hand and say that we found it, or the dog sits and makes the alert. If there's anything less than that, then we don't. Even though we might have some inkling that we are detecting it here, this is lower than our criterion that we set, our internal criterion that we set. So then we say, no, we did not detect it. And so this criterion here, as you can see, is someone who is what we consider more conservative. They have their criterion set well within the signal distribution, meaning that the signal has to be on for sure to some degree before they'll say, I have detected it. We can have people who are what we'd say unbiased, meaning that there's essentially no bias either to being conservative or to being liberal, but they actually have what we would consider optimal performance, which is their criterion is set right in the center between these two distributions. So this would be ideal unbiased participant here, meaning that a very minimal amount of your signal produces a response, and anything less than that is more likely to be within our noise distribution doesn't produce a response. So this is a figure from one of our more recent papers that I actually talked about in the last webinar, but it becomes relevant here. So this is when a dog made a miss during a search task. We had both sport dogs and professional dogs. We looked at, well, how long did they sniff at the target odor, where it actually was, even though they didn't alert there. And we compared that to how long did they sniff in a similar and what we would consider as much as possible an equivalent area that did not hold the target area, the target odor, which was a non-target odor or non-target area. So neither of them were alerted towards, they were both misses, but we looked at how long did they investigate, and both our professional and our sport dogs showed more investigation, even though they didn't alert to it, to the target odor than to the non-target odor. So to me, this suggests that in this particular situation, we had what I consider probably more conservative dogs. In other words, that there was some detection occurring because they were sniffing at it and showing more investigation to it there, but what they were detecting didn't quite meet that criterion threshold. It wasn't above it, so they did not alert to it. In fact, we're just below that criterion threshold. So there was some level of detection, but not really enough, which indicates here that, to me, what those dogs' internal criterion is probably an important thing to define and better understand. Okay, so now we can look at the exact same thing, but now with our figure where we have a very small d prime, so very little difference between our signal and noise ratio. So situations, and I guess a real world situation where this might apply would be, say for example, you are working your dog at near threshold detection levels. So your signal is quite highly overlapped with your noise because you're looking at very, very low levels of an odor. So there, when you're getting very close to threshold, or at threshold, your d prime goes to 0 so that the two distributions overlap completely. As you're getting close to the threshold, that d prime keeps shrinking, shrinking, and shrinking, and shrinking. So this would be situations where you're looking for detection of particularly low odors. So here's your criterion, which is ultimately, for this particular dog, if the criterion was here, we would consider them unbiased. It's right between that overlap between the two distributions. And now it sort of looks a little bit zoomed in before, and we can actually start looking at, well, what are the probabilities of different types of responses occurring? So if the criterion is here, that means anything to the right of this criterion the dog alerts on. Anything to the left of this criterion is what the dog does not alert onto. So this part that is blue right here, the area under this curve is going to be areas where the dog alerts and the signal is present. So this area right here these are going to be all of our hits. So the area of this curve here is the proportion of hits that we're going to get. This little area where you have that sort of red curve coming along, this is the noise distribution, and you can see that this is the criterion, meaning that they're going to respond to the noise within this distribution. So I'm going to change the color to dark blue here. So this dark blue here are going to be responses that the dog makes, but it's for the noise distribution. So this here would be our false alerts. Then, if we're looking at here is where the dog does not alert, but this is our signal distribution. So this green area are going to be our misses. So as you can see here, our misses and our false alerts are going to be quite substantial in comparison to what we saw when our d prime was much larger. So here, an example, as I said, of this would be like getting close to threshold detection levels. We're definitely expecting many more false alarms and hits, false alarms and misses, purely based off of the mathematics of the detection situation, not because there's residual odor, not because there's handler bias, not because there's some other thing that might lead to these, and we'll talk about these at the very end of this webinar. But these are the errors that are purely expected simply based off of the complexity and challenge of the task itself. And I forgot to note that this distribution would be the correct rejections here. And as you can see, when we have an unbiased observer, an unbiased dog, that the number of misses that we see and the number of false alerts that we see are about equal proportion, so that they have similar levels of false alarms and similar levels of correct rejections. So that's why we would say that they're unbiased. They're just as likely to say, yes, it's here when it's not there, as they are to say, no, it's not here when it is there. We can compare this to what we call perhaps a more liberal dog. So a more liberal dog might be a situation where you desire to train your dog to have more of a criterion that's more liberal. Maybe an example would be an explosives dog, where the risk of a miss could be quite substantial versus the risk of a false alarm being a very large inconvenience, but significantly less worse than the risk of a miss. So by moving this criterion off to the left, making us a more liberal dog, our miss area becomes this big, which is a very small area, but our false alarm distribution is all of this area. So as you can see, our false alarm probabilities go through the roof when our dog is more liberal in comparison to our misses, which are going to be very minimal. So this liberal dog, which we can modify a little bit through training, is going to have very few misses, which is great. But as a consequence of that, because the task is hard, that means that we're going to see substantially more false alarms from this dog. We could compare this to a more conservative dog, where in this situation, our false alarms are actually just this area. So we have very, very few false alarms, but perhaps, quite concerningly, we have all of these as misses. And what is the right answer? Well, obviously it's going to depend on your detection task, right? And ultimately what your goals are. If, for example, it would be a tragedy in your situation to have a false alarm, and that could have significant implications for you and your dog, then it would suggest that you would want to try and have a more conservative dog. And the trade-off then would be that you would have significantly more misses. Or perhaps a miss would be an absolute tragedy and it would be okay to tolerate more false alarms, so you would want a more liberal dog. Or perhaps you want the optimal balance of false alarms and misses so that you can minimize both at the same time, and there you want a dog that would be the optimal non-biased observer, which would be right here down the center. And the nice thing about these is that these are all purely mathematically calculable from performance data of your dog within a simple go, no-go task, which is nice, so that while I'm drawing these out as little curves, you don't have to draw these curves out. You'll be able to get objective D' and C data to look at how conservative or liberal is my dog simply based off of a series of tests that you give them. So a couple of highlights so far. So signal detection theory highlights that the importance of the detection task itself is paramount. So what that D' is absolutely paramount to what kinds of performances you're going to see. And then subsequently, that observer's internal criterion is going to be really important, because that's going to influence that balance between your false alarms and your misses. And that criterion can be influenced by a variety of external factors in your training. So if we think back to our TSA individuals, if you were the boss and you said, if you miss a weapon, you will get fired, right? That puts a strong motivation to become more liberal in your decision criterion, such that anytime there's anything remotely looking like a weapon, it would be much easier to have a false alarm, signal it, pull the bag off, look for it, search for the bag, and then give it to the person if you don't find a firearm. Or perhaps, there might be another situation where you would want to say you do not want to trigger a search unless you absolutely had to. So there you can put motivation to not have any alerts unless you're 100% sure that there's going to be something substantial there. You can do the same with your dog, essentially by changing what your rewarding properties are, right? If you are rewarding quite extensively for alerts, then you might have a more liberal dog who is going to be more interested in making alerts to a variety of things. If you, through your training, you make it quite costly for them to make a false alert, like so for example, if they make a false alert, they have to start all over from the beginning, or perhaps it's going to take, after a false alert, a long time before they have the opportunity to then go and search again, then these things would be substantially increasing the cost of a false alert, which might bias your dog to a more conservative perspective, so that when there are questionable situations where it's a little bit of a lower concentration, maybe the dog won't respond because you've made it costly to false alert. And we see this particularly potentially with if you have aversive methods to prevent false alerts, because now you're making it particularly costly for the dog to make a false alert. So then you might be biasing your dog to have a more conservative perspective so that they're only going to alert when they're 100% sure that that target odor is there. So false alerts and misses are real and totally expected. One of my general rules, very well could be wrong, but for the most part I find that I do not trust folks who indicate that their dog is never wrong, right? That the dog never false alerts, never makes any misses. They're always 100% right. Usually that means that the dog does make false alerts and the dog does make misses, but they always have a reason to explain them away, why the dog missed that time or why the dog made a false alert. So the point here is that it's 100% natural and expected for false alerts and misses to occur. You're not going to get 100% unless you have a situation where your D prime is so large that those two distributions don't overlap. However, in a lot of our situations, the noise of the environment and the noise systems that are going on and the distractions are going to be quite substantial. So we're going to expect some, but obviously we want to minimize those as much as possible, but we're going to expect some. And that's a completely natural thing. You're not going to get them down to completely zero levels. Unless if you wanted false alerts to go to completely zero levels, you can do that by shifting the criterion, but by doing that, you're going to be substantially increasing the probability of misses, like I showed before. So a false alert does not necessarily mean that there was residual odor. It could mean that the job is just simply hard for the dog to do, and that is perfectly fine too. To improve both false alerts and misses, the only way to do both simultaneously is by sort of shifting your, decreasing your noise distribution or shifting your signal distribution much higher than your noise distribution, meaning that you can remove distractors in the environment, you can remove complicating factors that are significantly decreasing or overlapping with your target odor or decreasing target odor availability, or you can make it easier by increasing target odor availability. Those would be ways that would increase both of them at the same time. Otherwise, you would have to make trade-offs. So if you optimize discriminability, but need to change false alerts or miss probability, you can adjust the dog's criterion through your reinforcement contingencies. You can make it highly rewarding for the dog to be more conservative or highly rewarding for the dog to be more liberal. Okay, so now I'm going to jump into a slightly more confusing topic. If you don't completely follow along with me, that's perfectly fine. But we'll break down some numbers into, I think, a topic that most people don't ever think about, generally speaking, unless forced to. So this is the importance of prior probability, or what is the likelihood that there actually is something there for my dog to detect. And it's actually quite interesting because that likelihood is actually a very significant contributor to whether, if your dog makes a response, whether it's likely to be true or not. So let's say, for example, we'll just take a scenario where you've trained your dog up and they've met a certification criterion of 95% accuracy, and they make on average 1 false alert out of 20 runs, which equates to 95% accuracy, so 5% mistake rate. And let's say you're working and you do 2 searches a day for 300 days a year, which would be about 600 days a year, and you do that for 2 years. So you have 1,200 searches you run across a 2-year span of time. So on the left group here, your dog's accuracy is 95%, and the right group, your dog's accuracy is 95%. In the left group, let's say that the probability that your dog will find something on any given search is about 30%. So maybe you're searching for something that's relatively high probability. But perhaps someone else's dog is actually searching for something with a really, really low probability. It would be like 0.1%. So say this would be something like explosives, right? Very rarely will they find something in a live situation. So you both run 1,200 searches over a 2-year period of time. Because of these 1,200 searches in a 0.01%, this group would only expect to find 1.2 explosives on average across that 2-year period of time, which even that feels kind of high, but nonetheless. If it was 30% on average in comparison, there would be 360 targets. 840 non-targets. That means that based off of a 95% accuracy, they would correctly have 342 hits, 798 correct rejections, 18 misses, and 42 false alerts across that 2-year period of time. And this is just purely, this is what we would expect based off of those distributions. Nothing to do with residual odor, or there was some mistake, or someone distracted them. These are just purely based off of these numbers. And in fact, if your dog is certified at 95% accuracy and doesn't make 42 alerts and false alerts and 18 misses, then you're probably fudging the data because this is just what we would expect probabilistically. But anyway, what this equates to is that when your dog makes an alert, on average, 90% of the time it will be correct. So when they make an alert, it will be 90% of the time there will actually be something there to detect. For a non-alert accuracy, so if the dog doesn't alert, then there's a 98% chance that there really wasn't anything there. We can do the exact same thing now with our 0.001 probability, and we produce these numbers. And on average, we would see 0.06 misses, so less than 1 miss within this period of time, which is hopeful, right? Because it would indicate that they found the one target that occurred. But you see that there would become about 60 false alerts. So the alert accuracy, interestingly enough, drops down to 1.8% or 2% on average. So if your dog makes an alert under these conditions, there's only a 2% chance that it's actually really an explosive. And there's a 98% chance that it is not an explosive. And this is purely statistically, that simply based off of this low probability, and say you were running this explosive dogs with this probability, and the dog alerted, there would still, and your dog was certified at 95% accuracy, there would still only be a 2% chance that there was actually something there. In comparison, though, if your dog doesn't alert on something, then there's a 99.999% chance that there really isn't anything there. So this is why the prior probability of whether something might actually be there or not is quite an important factor to think about when you're considering your overall dog's performance. So now I want to quickly go into some non-detection factors that are influencing performance. So these will be things that aren't really related to signal detection or simply detection in of itself, but are going to be more external factors that will also influence performance. And one of the first ones I want to point out is that dogs are not just odor detectors. Dogs are really detectors in all variety of ways, right? They're hearing detectors, they're eye detectors, but in particular, they are human behavior mastermind detectors, which can make it quite challenging, especially if the dog is always working with a person. Which means that outside of the signal detection approach, there can be factors like human behavior that can sort of superimpose and go on top of that could also be substantially influencing performance and the probability of a false alert. So as an example simply of the fact that dogs are super human masterminders, is just there's some fun studies about how dogs are super sensitive to how humans respond, and particularly with guilt. So a lot of us think that if our dog does something wrong, they look guilty. There's thousands of examples. If you search guilty dog on the internet, you get several pictures like this. You also get lots of pictures of aggressive looking dogs, scarily enough. There's actually some studies that have highlighted that the guilty look that your dog is making is actually most likely a response to your behavior when you notice the damage, rather than the dog making that response because they made that damage. There's some pretty clever experiments. There's a link to one of them here to highlight that. But the reason why I bring that up is that it really sort of highlights the fact that the dogs are super sensitive to our behavior, to the point that when we think naturally that they are responding to something in the environment, like they destroyed something, they're actually responding to our behavior, and they're just so good at it that we believe that in reality they're responding to the environment, but really it's just a response to how they're reading our own behavior. And this really highlights the potential for handler influence. I'm going to go through this quickly because we discussed specifically some of these slides in the last webinar. But we did see that in a previous study that dog sensitivity tended to be higher when they were working with a known handler versus an unknown handler. We do know from one of the key experiments by Lisa Litt et al. In 2011 that if you tell handlers that there are target odors whenever you see particular markers, that there's an increased probability that a dog will make a false alert or that they'll call a false alert when the handler is led to believe that there's a target odor there and they can see that marker versus when there isn't a marker. This ultimately sort of highlights the Clever Hans scenario, which I won't go into the whole story since I'm running close to time, but basically a very clever horse that, like the dogs, are quite adept at being able to read human cues and human behavior, and was able to make it look like the horse was completing a variety of complex tasks when in reality they were just responding to the person who was giving them the tasks. So this is the data from the Lisa Litt study, which highlights that when you marked the decoy and these marked conditions, you tended to see more false alerts. So you're seeing larger false alerts here and in this condition than when you were in the unmarked condition. Importantly, it's not completely universal, right? There's certain individuals like this one that made no false alerts across the entire study, but then you also have, some that made lots of studies even when there wasn't a marker. Sorry, lots of false alerts even when there wasn't a marker. And then we did our own study that recently came out. We looked at professional and sport handler dogs, and we assigned them to groups where they knew how many hides were present versus groups that didn't know how many hides were present, and looked at performance differences between the two groups. And one of the key things that we found in that one is that in that situation, when certain individuals knew that there were exactly only 2 hides and 3 search areas, we didn't see differences in the overall levels of false alarms for both sport and professional organizations, despite knowing some individuals that there were no additional odors present because they were told that there were only 2 there. So the potential for handler cueing is definitely there. It's been demonstrated in the Lisa Litt studies. It's been demonstrated by Clever Hans. We know that the dogs are sensitive to our behavior through the guilty look kinds of things. But in particular, when it seems like the situation might be ambiguous, that the handler doesn't know one way or the other, versus they have some information of the task, it doesn't influence as false alarms. The study did find that there were several other influences on the dog's search behaviors. And this sort of brings up another question that we commonly get or see is, well, what about the potential for residual odor to be the cause of false alarms? That's certainly a potential, by all means, and it definitely, the scientist's answer is it depends. One of the reasons it depends is, well, what type of equipment are you using? How are you cleaning it? If you're using something that's highly porous and highly absorbable like wood, not to sort of criticize anyone, I just pulled this picture off the internet, then there is quite a potential that you might be having significant residual odor, because once you put an odor in this box and it's in a porous environment, it's not clear how long that odor might be retained within that box, even if you take things out. And then a potential problem is that then if you always use this as the hot box, then how do you know that the dog doesn't just slobber all over this one, or that there becomes a mark somewhere else and then the dog is just learning to follow this specific box and not the target odor. So there becomes several problems within these potential scenarios from a training perspective. But at the same time, there are definitely situations in which there is not residual odor because you were able to systematically clean your system, you were able to reduce potential contamination. So it definitely, the answer is it depends. However, if you're not cleaning and properly maintaining and storing your your target hides or your boxes that you're using, this can be problematic because perhaps it might change the dog's criterion. So say, for example, this was the box that was used as the hot box yesterday, so it has lots of residual odor, obviously not as concentrated as this box where it currently has a target odor. Say the dog comes up and alerts here. You're thinking, oh, the target odor is not here, so you're not going to reward this, right? So now the dog has, and then you take the dog off and do a research. So now we've imposed a sort of a cost to the dog to alerting to something that was a low concentration. So in this situation now, this is suggesting that perhaps we're shifting the dog to have a more conservative criterion, such that they're not going to respond to things that smell close to it or perhaps low concentration, because if they learn that you don't want them to respond to that. So this would be a potential problematic area for that. So this is what that spells out. So if you train with contamination and the dog falses, they learn to not respond to the weaker stimuli, which is then shifting their criterion to the right, which is making them more conservative, which is then introducing the potential for a lot of misses at lower concentrations. So the probability of a miss increases, and interestingly enough, I also point out that chances are you're actually none the wiser, because in real world situations, unless it might be an explosive or something like that, but if it's narcotics or something like that, you don't really know if there was a miss, right? The drug dealer is not going to come back and say, I can't believe you missed this, right? So in a lot of situations, you can be none the wiser. So it's particularly important to, in your data collection system and in your typical routine testing, that you're identifying what perhaps your depriming your criterion is, to make sure that you're optimizing it to where you need it to be. It's also important when you're thinking about residual odor to remember that your dog is real, right? And that they're detecting real chemical stimuli in their environment. Your dog is not magic. They can't detect everything at all times under every circumstance. And mistakes can frequently be real mistakes, right? So one of the points of this is that based off of signal detection theory, false alarms and misses are going to be an expected part of performance. So if they happen, then it very well can be real, and you don't need to necessarily explain it away as residual odor. But as I just said, you still want to be careful and make sure that you're reducing as many of those kind of nuisance noise variables, and making sure that you're paying particularly careful to reduce the potential for residual odor, so you don't have that incidental of changing that dog's criterion in non-optimal ways. So that it's important to be realistic and understanding of what your dog's performance should be based off of some of these measures, and then subsequently making sure that you're still trying to reduce those noise distributions and avoid residual odor contamination that might be producing false alerts. And there it's even hard to say, is it a false alert or not? But if you start training the dog that they are incorrect, then you're shifting their criterion, which then makes them technically false alerts. I think it's also important, I've never actually seen this movie, but when I Googled Think Like a Dog, this came up, to also think about that your dog is going to be sensitive to a lot of other training patterns and routines that you do that are going to be completely irrelevant to the actual detection task in of itself. So let me give you some quick examples. So I say think like a dog. Think from their perspective. Why do they search? Ultimately, it's to get that terminal reinforcer, whether it be Kong, chew toy, food, at the end of the search for finding their target. But also the search in of itself can become conditioned reinforcement, and they enjoy doing that search because it's been associated with getting that terminal reinforcer, and then the search in of itself takes on reinforcing properties. But ultimately, it's going to be that terminal reinforcer that they're particularly paying attention to. So in that sense, really they could care less if they win or they find the object, whether they're using odor, vision, auditory cues, handler cues, or just learning some general pattern or some general trick to the entire system. And generally speaking, the harder the task, the more incentive there is to cheat. So the harder it is for them to get the answer themselves by using olfaction, and you start going down and dialing down to really low concentrations, all the more incentive there is to find an easier way out, some type of cheat within the system. So if you're working on those particular tasks like medical detection dogs, things like that, diabetes alert dogs, seizure alert dogs, those dogs have extreme incentives to cheat because they're doing incredibly difficult tasks. So the distribution differences, their D prime can be quite small. So if they can find a way to more accurately and faster identify the difference between what you're training them as a positive and training them as a negative, then they will, because it gets them to their terminal reinforcer at a higher frequency. And other things that might be general pattern related is or why the dog might start engage in certain behaviors. Well, what happens if your dog doesn't find anything? Do they just get back in the car? Do they go home for the day? So if the dog is going through a search and it's been a while without finding anything, and the response to not finding anything is, I'm just going to get back in the car and not do anything, then maybe there's incentive there for the dog to at least try to alert, particularly if the dog was already had a more liberal criterion to begin with. And then is there always at least, say, for example, one find every 3 searches? Is there some pattern to what you're doing that the dog can pick up on, that if I didn't find anything in the first 2 areas, then that means that there must be something in the 3rd area? Is your hiding random? Perhaps you're always hiding it in the exact same 3 spots, but you didn't realize it because you're not tracking it. Humans like to particularly hide things either in the middle, at the far beginning, or at the far end, which makes those, if you're doing a lineup, those areas particularly popular because we like to put them there. Also, we tend to forget that or misunderstand randomness. So say, for example, you put your odor in position 2 for trial 1. A lot of times we want to switch it to, say, position 3 or position 4, but in reality, according to a random pattern, it very well could be in position 2 again the next time. But we just don't think that that would be right from a randomization perspective, even though from a randomization perspective, that would be quite possible. Also, do you distribute blank runs randomly instead of not always doing a blank run as either your first thing or your last thing, or maybe once every 6 months or something like that? Is the dog getting frequent experience with going through searches where they're not finding anything? And what is their response under those situations? Is it to false alert that they didn't find anything? If it is, then that's suggesting that you might have some of this issue where your dog is simply, there is no option for them to get their reinforcers, so they may as well try to alert to something. So we actually saw some evidence for this, mostly in our sport group. We didn't see it so much in our professional group, that when the dogs were on a longer search, or it wasn't necessarily a longer search, we looked at how long did it take for a hit to occur and how long did it take for a false alarm to occur if they made a response. And it seemed that, interestingly enough, falses were occurring at the very end of searches versus hits occurring quicker. So the dogs would quickly go find the target odor and alert if they could find it. If they couldn't find it, they would keep searching, keep searching, keep searching, keep searching, and then it would be later in that session is when the false alert would occur. So perhaps as the search drags on, false alert likelihood increases because the dogs are identifying that there's not, I don't see anything here, so I may as well try and alert to something to see if I can get the reward. Another sort of interesting topic is, can you tell if something is real or not? Can you look at the dog's performance and say, yes, this is a false alert, or yes, this is a real true positive, or perhaps this is a false negative? There actually have been a few papers on that. So one is the one I already described earlier from us, which was looking at when a miss occurred, how long did they investigate a target versus a non-target. So both of these were a situation where a miss was This is what we would call a correct rejection, or according to this study, a true negative. So that the dog, there really wasn't any target odor here, and they sniffed for a very short period of time there. But here would be a miss where the target odor was, so this would be a false negative. Where you can see from our study that the false negatives occurred, there was more sniffing to them. They spent more time sniffing where the target odor was versus where the non-target odor was. And there was another paper by Concha et al. That actually found very similar patterns of results, where their false negative here was about 0.4 seconds and their true negative was about 0.268 seconds. And interestingly enough, we didn't have enough data to be able to do the subsequent analysis, but their true positive, so actual hits, was about 0.5 seconds, and their false positives were also about 0.5 seconds, which suggests that you can't really tell the difference perhaps between a false positive and a true positive because those tend to be quite similar, but you can definitely tell the difference between a true negative, meaning that there is nothing there. They tend to sniff that for a very short period of time. There's a more recent study in rodents that came out that looked at different dilutions of the odor. So this is decreasing in concentration on our x-axis. So here, as we go over here, that's very low concentrations. And if we look at their accuracy, we see that they're doing great. Their performance starts to decline. And then once they get here, their performance is really bad and very poor performance at these low concentrations. But I want to point your attention to the sort of sampling duration, sniffing-wise, as a function of what the performance was. So for hits, when the odor is present, they tend to sample and sniff it longer under most conditions. If it was a correct rejection, a false alarm, or a miss, when the task is easy, those all look the same. And they all tend to be less than a hit. So if they make a false alarm, if they make a correct rejection, that tends to be a much shorter sniffing period. However, as the task gets harder, right, accuracy is going down, what you tend to see is that the falses and the misses tend to increase in sniffing duration so that it looks all the same as a hit. But interestingly, the correct rejection stays here with very low sniffing sampling times, which again replicates what was found here, which again replicates what was found here. So interestingly enough, that seems to be perhaps more consistent across studies, is that when there really isn't anything there, then the dog just doesn't sniff, or this one was rodents, but the animal doesn't sniff there as long. Particularly though, in this case, when it's a hard detection task. When it gets too hard of a detection task, then it all looks the same. There's no way to tell the difference between them. So ultimately the answer is yes to some degree, but also with lots of caveats with it depends on how hard the task is. And ultimately it does seem though that at least false positives and true positives are sniffed at similar rates, perhaps suggesting that when false positives occur, it is because they really seem to be responding as though they are detecting something, that there is something interesting there to smell, which means that it would be very difficult to determine whether you're seeing a true positive or a false positive from there, simply based off of sniffing frequency and duration. But I also, I forgot to point out though, that they did see at the bottom figure that when a false alert was occurring, the rodents sort of ran to the ring enforcer more slowly. It took them longer to get there than when there was a hit there. It would suggest that there was some separation between them, which might, we don't have any data from any of the dogs to do this, but it might suggest that perhaps the dogs might show a more hesitant alert when they're making a false alert versus a hit. But obviously this is a very, very tentative guess. I would not consider that scientific by any means, but there does seem to be that little bit of evidence from the rodents from that paper that would suggest that that would be something worth investigating in dogs, most definitely in the future. Okay, So to finally wrap up, false alarms and misses are natural and expected. They depend on the deep prime and the difficulty of the task and what your decision criterion happens to be. Both can be influenced by task conditions and previous training experiences. There's also potential for a variety of external factors that can influence performance. Do dogs learn patterns in your training? Is it worth it to false anyway? Or are they encouraged to only sort of respond to really high concentration odors because they've learned not to respond to low concentration odors because of residual odors, a variety of sort of things like that. So it's an amalgamation of things. And then lastly, correct rejections seem to potentially look different than misses by having a shorter sniffing duration, but false positives, misses, and hits seem to look quite similar in terms of sniffing duration across the study shown. So overall, that's what we show. So there's lots of caveats that are going to be looking at false alarms, misses, any kind of incorrect responses in the dogs. But hopefully this gave you an introduction into a lot of the mathematical theory behind it, highlighted that there are ways that we can quantitatively evaluate this, identify what are your expectations based off of these theories like signal detection theory to hopefully better inform your expectations for training. Hopefully that wasn't too much and somewhat informative, and I look forward to taking questions.